Now, if the buckling load is much greater than 36, the yielding load, that means the structure will not buckle, but will yield first. However, what if we change the height? What if we do this? Suppose I increase the height to become 200 inches. So let's try this value. If the length now becomes 200, actually you only divide it by 4, and this value is still large. And that's good, not good enough. So let's try 400. Now, if the length is 400 inches, the critical load will be reduced by the length square, which is 16 times. That means the new critical load will be 1/16 of the original ones. In that case, PCR is...
I have the number. It's 1,490.72.
Yes, thank you. And let me double check that. So in this case, if we increase the height or increase the span of the column, the critical load, or the buckling load in this case, will be reduced drastically. That means what? That means if you use a 100-inch column, so this corresponds to 100 inch, and the other value is somewhere here, which is 1.5. And that corresponds to a 400-inch column. What we learned from this example is this. The yielding force will not be affected by the geometry of the column, right? Because the yielding force is just the product of the yielding stress times the cross-section area, which is this equation here. It has nothing to do with the height or the length of the column. But if you change the length of column, it's going to affect the buckling load. So one lesson we learned from this example is that buckling has something to do with the dimensions, not the cross-section area, but the length of the member. So that's what we know. Okay, any other questions about this one? All right, let's come back to the slides. Now, materials can fail briefly, or ductile, or fatigue failures. And the structural failures usually can be caused by the change of the geometry. And this change of geometry from structural stability, you will learn that not only the length of the member will affect the buckling load, but also the boundary condition can also affect the buckling load. And just few pictures to show you that when buckling occurs, what happens to the structures. And you have some experience from engineering materials lab. You have seen how material samples, material testing coupons fail. But when you scale it up from the materials level to the structures level, the result is even more catastrophic. When buckling occurs, there's nothing to stop it, because buckling indicates one type of failure which does not require the structures to acquire additional force, but then the structure will find a way to exhibit excessive deflection. That concerns structural engineers.
Professor, I have a quick question regarding the previous image. It says note temperature minus 54 degrees Fahrenheit. Would that be considered that the temperature greatly affected or influenced that buckling?
Yes. And how does the temperature affect the buckling? The temperature affects the Young's modulus. So when the temperature becomes very low, the Young's modulus becomes reduced. And that's why the structure fails this way. A very good observation. However, you also remember the previous slide. To assess the potential of a structure against buckling is usually the combination of materials property as well as its own loading condition. In this particular case, what we know is that the temperature definitely is partially responsible for the buckling failure of this wind turbine tower. However, what we did not know was what was the loading on this wind turbine tower. Right. What we know right now is that it fails due to buckling, but maybe it's because of the temperature. Maybe it's because of the wind was excessive, and that's why I put it here. Sometimes excessive loading can also trigger buckling. And today, engineers use computer softwares to assess the buckling potential. However, this kind of numerical simulation usually taken place by the use of what we call finite element method. And you can also learn finite element methods from another graduate level class. Finite element method allows engineers to create this kind of simulation to understand the local stress distribution. You can also only use it to assess the potential of local buckling, but you cannot use finite element simulation to assess the potential for global buckling, which is why you need to take structural stability, because for global buckling, finite element will not predict buckling. It will only gives you the predicted stress, but it will not tell you that there will be buckling. The best tool to assess buckling is usually through the hand calculations that we will talk about in this class. Buckling can occur everywhere. And in this case, is what we call torsional buckling for beam elements. You can see that the torsional buckling actually, this is also what we call lateral torsional buckling, is associated with the excessive bending on the flange of the beam, as well as the warping deformation on the web of the beam member. Buckling can occur not only to members, but also to structures. And this kind of failure is today we call it colossal failures, because buckling means a sudden drop of the bearing capacity. And if a structure system is a lack of sufficient redundancies, once a critical member buckles, it will lead to the total failure of the structure. And again, at the moment, this kind of failure will happen very, very fast. As a structural engineer, you should know that we do not want to see these kind of failures happen. You have learned how to design and analyze the structures, but this may be the first class you will learn how to predict the failures of structures. Conceptually, structural engineers want the structures to fail with certain amount of deformation, and that deformation should take time. In other words, certain failures of structures is an absolute no-no in our business. We absolutely do not want structures to fail all of a sudden. You would rather to see that before failure, the structure system will exhibit some large and most importantly, measurable deflection. And we will use it as a sign to provide structural repair or even to evacuate the structure just to protect human lives. If you look into the engineering literature, there are lots of structures that will fail due to buckling. And one famous example back in 1987 was the Husky Stadium. Of course, because at the time, structural engineers did not know that the coupling of two different buckle modes could actually lead to the global failures. In this case, lack of redundancy was also part of the reason why this stadium made of steel structures failed. As you can see that when the buckles occurred, and the total failure will follow, and that usually takes place within a few minutes of time. When that happens, there's no way to stop it.